Hi everybody, this is the lecture on section 4.3, partial derivatives. Recall the original definition of the derivative of a function f prime of x. Right, that is that f prime of x is equal to the limit as h goes to 0, f x plus h minus f x over h. Okay, geometrically, f prime of x represents the slope of the graph, the slope of the tangent line to the graph y equals f of x, for a particular value of x. Right, so the old picture is, right, you've got your function smooth and continuous for the derivative to exist, and say this is the point A, f of A. Right here, the tangent to the graph at that point, the tangent line to the graph at that point has slope f prime of A. There we go. Probably I didn't quite draw the graph with that slope. Let's redo it. There we go. Alright, so the slope there is f prime of A. Okay, can we do something like this for two variable functions and three variable functions? Now consider a two variable function z equals f x y. Define the partial derivative with respect to x as the limit as h goes to 0, f x plus h y minus f x y over h. So in this limit, the x is varying because you're adding h to the x component. The y is staying constant. So treating y as a constant, so the limit, not that you choose to do that, it is that. The limit treats y as a constant and only x varies. Right? Thus, I should give it a notation. It's so the first notation that one uses is f subscript x, xy. Partial derivative with respect to x. Okay? Thus, fx, xy is calculated as usual, in which y is thought to be a constant. It's the same definition as before. It's just you've got this letter y hanging around, but it's a constant anyway. So you just treat it as such. Now, before I give some examples, let's do the first partial derivative with respect to y. It's defined the same way. And this is 2. The first partial derivative with respect to y is treating x as a constant. You vary the y by adding h. F of x comma y plus h minus f of xy over h. The limit treats x as a constant and only y varies. Thus, the notation is f subscript y, is calculated as usual, in which x is treated as a constant. So, for example, let f of xy equal x to the third y squared plus 2x minus y, sine of y. Right, then the first derivative with respect to x, and you can just kind of drop the xy to simplify the notation. Y is a constant, so y squared is a constant. So the derivative is 3x squared times the constant y squared. X is just treated as the variable, y is treated as a constant. So when you have a constant, you just take the derivative and leave it multiplied by that constant. 2x, the derivative of 2x with respect to x is just 2. And the derivative of sine y is a constant. So sine y is a constant, so the derivative is 0. So the derivative with respect to x is 3x squared y squared plus 2. The partial derivative with respect to y is treat x as a constant, y is the variable. So this is 2x to the third y, right? The derivative of y squared is 2y. And then you're just multiplying 2 by that constant, x to the third. The derivative of 2x, x is a constant, so the derivative of 2x is 0. Minus the derivative of sine y, cosine of y. Right? So, calculating these partial derivatives with respect to x and with respect to y, it's the same as what we have done before. There's no difference. Just you have another letter you just have to account for while you're working the derivative and just make sure you treat that one as a constant. Geometrically, what do these represent? These partial derivatives represent the slope of the curve z equals fxk for a specific value of x and k. The curve z equals fxk at x and z equal to fky at a certain y. Okay, so for example, if you take that surface that we had drawn from before, here it is. Oops. So here's that surface idea right here. Represent the slope of the surface, let's just write it this way, of the surface z equal to fxy in the x direction and in the y direction. So here's how to think of that. Okay, so here's that surface. So now let's take a point xy in the domain. So here's a point xy in the domain. And that goes up to a point on the surface. Okay, now this is going to be the curve. Make this thicker. Where y is held constant. And this is going to be the curve where, no, not where x is held constant. And this is going to be the curve where y is held constant. Let me make that one blue. Light blue. Okay, so the blue curve is z equal to fxy, that is, y is constant. And the purple curve is z equal to fky, that is, x is held constant. Right? X is held constant, and then we vary y. Right? Y goes in that direction. So x is held constant, and we're varying y. For this one, y is held constant, and we're varying x. So there should be a slope there. Let's see, should we make them... Yeah, so the slope of the yellow line it's kind of hard to see, isn't it? Orange. So the slope of the orange line is the slope of the blue curve. So slope is equal to, well, here x is varying and y is held constant. So the slope is the partial derivative with respect to x. Let's write it like that. Right? It's the slope of the blue curve. The slope of the purple curve, this ice color here, this leapfrog color. So Whoa. The slope of the purple curve is this green line. Slope is Fy. So the purple curve, you're varying y, and x is held constant. So the slope of that purple curve is the partial derivative with respect to y. And that's the derivative of that surface in the direction of the y-axis. When x varies and y is held constant, you get this blue curve. So this orange line has slope. So the slope of the blue curve at that point is the slope of this orange line. And that slope is the partial derivative with respect to x, because y is the one that's held constant. Okay, so there's the picture for partial derivatives. So you have slope in the y direction, slope in the x direction. Later on, we'll have slope in any direction, right? I mean, these two lines form a plane, right? Two lines, they form a plane, uniquely. And that plane is what's known as not a tangent line anymore. Now we have a tangent plane. And in that tangent plane, you should have slopes in any direction. This direction, this direction, this direction. So far, we only have in the x direction and the y direction. So the I direction and the j direction. So far, we only have those two. But later on, we'll have any direction, any unit vector direction that we want in the xy plane. And that'll be the directional derivative, and we'll talk about that later. Okay. Okay, so other notations, these are important. For partial derivatives. So just as given the function y equals f of x, right, we write the derivative as, right, f prime of x, or dy dx, right? This is the differential notation. We also have the differential operator right, d over dx, where d over dx, when multiplied by f of x, gives you the derivative. Right? It's an operator. The action is you multiply the differential operator times the function, and the product is the derivative. So we have similar stuff for partial derivatives here. Given a two-variable function, so similar to this, given a two-variable function, f of x, y, I'm sorry. Given y equals f of x, as there's three things we write. F prime of x, right, or y prime, or dy dx, y prime, right? Sometimes we just dispense with the f entirely and we just write y prime. Similar, given a two-variable function and the equation z equals fxy, we write the partial derivative as Well, there's the partial derivative with respect to x. Or sometimes you just write z, partial derivative of z with respect to x. Just dispense with the f entirely. Or what's the differential notation? You don't use a d. D, use this thing. It stands for partial derivative. It's kind of like a backward 6. Partial derivative with respect to x. And, so that's for the partial derivative with respect to x. And you also have partial derivative with respect to y, which is written f subscript y, or z subscript y, or partial of z with respect to y. And then we also have the differential operators. Partial with respect to x and partial with respect to y, like this, where the product partial with respect to x of fxy gives you the partial derivative with respect to x, and the product of the differential operator ddy times fxy is the partial derivative with respect to y. Same ideas as before, except we don't use a d anymore. You have this funny del operator, it's often called. So for example, if I had, so let's do a 3-variable function. All right, similar notions hold. For 3-variable functions. W equals f, x, y, z. Now you've got 3 variables, x, y, and z, and the function is w, is set equal to w. So, for example, given w equal to x squared, y to the third, z cosine z, like that, plus z squared, say. The partial derivative with respect to x. So I tend to use the differential notation a lot. Okay, the differential notation is clearer because you've got so many variables floating around. I find that it works out better. The partial derivative with respect to x of w. So here, y is constant, z is constant. Just x is the variable. So it's going to be 2x, derivative of x squared is 2x, times this constant, y to the third z cosine z, plus 0. The partial derivative with respect to y of w is equal to, well, 3y squared. 3x squared y squared z cosine z. All right, it's just 3y squared times that constant, in whatever order that you want, because multiplication is commutative, plus 0. There's no y there. Right? Z is a constant. And the partial derivative with respect to z of w. Well, I got z cosine z, so I need the product rule times that constant. So derivative of z is just cosine z. Derivative of z times cosine z plus z times the derivative of z, which is minus sine z. Plus all that multiplied by x squared y to the third, plus 2z. All right, so you've got these 3 partial derivatives with a 3-variable function. Now they don't necessarily correspond to slopes anymore. That notion just goes away, right? Because we don't have this visual representation of the function anymore. So talking about slope is really goes out the window. All you can say is that the partial derivative with respect to x represents the rate of change as x varies. The rate of change as x is varying and y and z are constant. The rate of change of w as y varies. right? And x and z are held constant. The rate of change of w as z varies and x and y is held constant. You can just think of them as rate of changes now. You don't have that geometric interpretation anymore. Although when we get to directional derivatives, you will. There will be a very special geometric interpretation for these partial derivatives. Well, as a whole. You'll see when we get there. Higher partial derivatives. So you can take partial derivatives in succession. Can be taken in succession. Right? So, for example, right, given f, x, y, the partial differential operators like this. So this is the partial derivative of f. First with respect to y. So first you take the partial derivative with respect to y. Then what you got left there, you take the partial derivative with respect to x. And then what you got there, you take again the partial derivative with respect to x. And this is usually just written as fyxx. Right, and you can just keep taking partial derivatives in whatever order that you want. Now there is, so here, like this, or if I did this, if I said partial with respect to x, just take a second derivative. Right, this one, sometimes we'll just write it like this in differential notation. Partial x, partial y, or partial with respect to x twice, you could just write partial squared f with respect to x squared. So that differential notation from Calc 1, it carries over here, pretty easily. Now, one thing you might notice is, remember, we write this multiplicatively, this differential notation. And multiplication is commutative. So did we take the derivative with respect to x first or y first? Well, when you write things multiplicatively, dx dy should be the same as dy dx, because multiplication commutes. So it's not really indicating which one went first and which one didn't, and which one went second. But it doesn't matter, okay? They're usually equal. And that is known as Clairaut's theorem. And Clairaut's theorem essentially goes like this. If a two-variable function f, x, y, z, or f of x, y, or three-variable function f, x, y, z, has continuous first partial derivatives, then f partial of f with respect to x and then with respect to y is equal to the partial derivative of f with respect to y and then with respect to x. Okay, so it doesn't matter which one you do first, as long as you have continuous first partial derivatives. Now, we didn't exactly talk about what continuity meant with two variable functions, but it essentially means the same thing as it does with single variable functions, is that the graph is unbroken. It's continuous. There's no holes, there's no rips, there's no asymptotes, that kind of thing. Okay? And, with most of the functions that we deal with, sines, cosines, exponentials, and polynomials, those things are always continuous. Okay? Normally in this type of calculus that we're doing here, we just deal with continuous functions. So let's take an example, okay? We'll say f of x, y is equal to square root x squared plus y squared. Now, you'll notice that the domain for this is all x and y except 0, 0. But it's a polynomial. X squared plus y squared is a polynomial. And a square root functions are continuous as well. Or should we say, a equals square root b. That's a continuous function. And polynomials are continuous. And compositions of continuous functions are continuous. So this is all nice and continuous anywhere on the domain, which is all x, y, except 0, 0. So, right, the partial derivatives, when you take them in different orders, should be the same. So let's find all first and second partial derivatives, verifying that fxy equals fyx along the way. Oops. Okay, so, well, fxy is equal to x squared plus y squared to the 1/2 power. So, partial derivative with respect to x, here's the first partials derivatives. First partials. F with respect to x is equal to, well, it's 1/2 x squared plus y squared to the negative 1/2. Times the derivative of the inside with respect to x, 2x plus 0. Right? So we have x over square root x squared plus y squared. Partial derivative with respect to y, well, it looks exactly the same. I mean, this is a function that, the roles of x and y can be changed, right? It's kind of symmetric with respect to x and y. So you get the same thing, blah, blah, blah. It's equal to y over square root x squared plus y squared. So that's the first partials. The second partials, well, you can do fxx. So take the partial derivative of this with respect to x. Right? So this is negative 1/2 x squared plus y squared to the negative 3/2, right, times the derivative of the inside, which is 2x, times x, right? You need the product rule, the derivative of the first times the second, plus the derivative of the second, which is just 1, times the first, which is x squared plus y squared to the negative 1/2 times x. Wait. Let me do it a little differently. Let's do it using the quotient rule, I think. It'll be a little easier. The derivative of the top times the bottom minus the derivative of the bottom. So that's square root x squared plus y squared, and the derivative is that with respect to x. Times the top, which is x, over the bottom squared, which is just x squared plus y squared. Factoring out a square root here, 1 over the square root, this is equal to, well, I guess, let's see, let's add them together with a common denominator. This becomes x squared plus y squared minus x squared over square root x squared. Yeah, there we go. So this is equal to positive y squared over x squared plus y squared to the 3/2. Let's see, I need a little more space to write that. right? So I added these together with a common denominator, which is square root x squared plus y squared, and it looks like this, which is equal to, in the end, bringing this down here, y squared over x squared plus y squared to the 3 halves. So that's fxx. fyy, it follows the same pattern, and you get x squared over x squared plus y squared to the 3 halves. I mean, the reason why I know this, again, is because the original function, right, the roles of x and y can be changed, and it doesn't change the function. If I switch x and y, it's the same function back. So whenever I take the partial derivatives with respect to x, it's the same as taking the partial derivatives. It's analogous to taking the partial derivatives with respect to y. Now how about fxy and fyx? So the partial derivative with respect to x. Now we're going to take the partial derivative with respect to y. So this is the partial with respect to y of x over x squared plus y squared, square root. So, using the quotient rule, it's the derivative of the top. Well, let me rewrite that, actually. It's the partial with respect to y times, x times x squared plus y squared to the negative 1/2. The x is a constant in this calculation. So, we're just taking the derivative of the x squared plus y squared to the negative 1/2. So that's negative 1/2 x times x squared plus y squared to the negative 3 halves times the derivative of the inside, which is 2y. So this 2 and this 1/2 cancel, and I get minus xy over x squared plus y squared to the 3 halves. So that's the partial derivative with respect to y of the partial derivative with respect to x. If I were to do it the other way around, Clairaut's theorem says we should get the same thing. It's the partial derivative with respect to x of this partial derivative with respect to y. So partial with respect to x of y times x squared plus y squared to the negative 1/2. So this is equal to, and y is constant, negative 1/2 y, x squared plus y squared to the negative 3 halves times the derivative of the inside with respect to y, which is 2y. The 2 and the 1/2 cancel, and we get which is 2x. And we get minus xy over square root over x squared plus y squared to the 3 halves. And this are the same, as they should be. Okay, nicely continuous functions with continuous partial derivatives. It should be that the partial derivatives can be done in any order. So partial derivative of f with respect to x and then with respect to y should be the same as the partial derivative with respect to f with respect to y and then with respect to x. And here's an example of that right there. Okay. With 3 variable functions, the same sort of thing holds. So for example, let w equal x squared y to the 3rd z to the 4th. Right, so let's do partial derivative of x with respect to z. Let's do partial derivative with respect to x. So that's 2x, y to the 3rd, z to the 4th. Partial derivative of w with respect to z is 4x squared, y to the 3rd, z to the 3rd, like that. Partial derivative of w with respect to x and then z is going to be equal to, so I take the derivative of this with respect to z, and I get 8xy to the third z to the third. Partial derivative with respect to z and then x, take the derivative of this with respect to x, and I get 2 times 4 is 8xy to the third z to the third, and these are the same. wxz equals wzx. And, this is a polynomial in 3 variables. Polynomials are all nice and continuous. So the partial derivatives are polynomials, which are all nice and continuous, and therefore we should expect Claro's theorem to hold. Well, we know that Claro's theorem will hold, and the partial derivatives can be done in any order. X with respect to x, and then with respect to z, or with respect to z and with respect to x, gives you the same thing. Or like, wxx yz or something like that is going to be equal to wyxzx. Whatever order it happens in, you get the same result. Okay? So that's all for our lecture on section 4.3.